In section 9.7, we're going to start talking about Taylor polynomials. So these are a really important topic in our BC Calculus course. Right? A Taylor polynomial is a polynomial approximation of a given function. It can be an approximation of another polynomial. Typically, the practical application is it's a polynomial of some transcendental function, like an exponential or a trigonometric or something like that. We're going to develop this idea kind of from the most basic level. So we're going to really build up to this. It's going to take a little time, so bear with me. You may need to kind of review or rewind and watch this again. But this is one of those things I definitely hope that you come to class with some questions on, so we can continue this discussion. I don't expect this discussion in the video to be kind of the be-all, end-all. So say I have some unknown function f of x, and I want to make, we're going to start with a linear approximation. So we're going to call that p of x. I want to have a linear approximation of f of x at a certain place. So I'm going to say at x equals a. All right, a linear approximation, that's just, we know from early in the first semester, a linear approximation of this function at a certain place is just the equation for the tangent line. All right, so what makes a quote-unquote good linear approximation? Well, the point on our linear approximation has to match up with the point on the original function, right? Our linear function has to pass through the function, the point on the original function. And the slopes have to be the same. So the slope of our line has to equal the slope of the original function that we're trying to model at x equals a. All right, so we know that the value of the functions have to be the same, and the first derivatives have to be the same at x equals a. Obviously, they're not the same other places. They're just the same right there. Okay, so our linear approximation is we start with the f of a, and we add f prime of a times x minus a. And this gives us our linear, the equation for the tangent line. All right, so let's extend this idea, and I want to develop now a quadratic model for the same function. Okay, so I'm going to say the quadratic model looks like this. It's some quadratic with coefficients. So I have a x squared plus bx plus c, and I want to model that function f of x at the point x equals a, and of course it has to go through this point again, so it's going to go through f of a as well. All right, so the conditions for a good quadratic model, just like for the linear model, we needed the functions to be equal, we needed the slopes to be equal at that value of a. For a quadratic model, we're adding on another condition to make it a good quadratic model, and we're going to say, okay, well, not only do the functions have to equal each other at x equals a, and the first derivatives have to equal each other at x equals a, but the second derivatives also have to equal each other at x equals a. All right, so let's start off. We're going to take this q of x and find the first and second derivative. We're going to have to deal with the first and second derivatives here eventually, so let's find them up front. So just in terms of a, b, and c, the first derivative is 2 times a to the 2 times a times x to the first plus b, and then the second derivative would be the derivative of that. Derivative of b is 0, derivative of 2ax is 2a. All right, so we're going to work and we're going to figure out what these coefficients might be, this a, b, and c. All right, we know right here that the second derivative of q equals 2a, and we know that the second derivative of q at a has to equal the second derivative of f at a. So if q of x is equal to 2a, then f prime of a must also be equal to 2a. So a, we can solve for a. We get a equals the second derivative of f at a divided by 2. So we have one of our coefficients right there. If we look at the first derivative condition, we found here that q prime of x was equal to 2 times a times x plus b. That means that the first derivative of q evaluated at a equals 2 times a plus b. That is where this came from right here. All right, and we know that the original function's first derivative at a has to equal our model's first derivative at a. So we take our a that we found in the previous step, we plug that in, second derivative of f at a over 2, we got that from here, plus b. And then we can solve for b, so we get b is f prime of a minus a times f prime of f double prime of a. All right, you can see that these two 2's cancel out here. Then we solve for b. So we have an expression for a, we have an expression for b. Now we're going to work on the expression for c. So c is going to come from the function values themselves. So q of a equals a times a squared plus b times a plus c, and that's going to equal the function value at a. All right, we have expressions for a and b. We're going to plug those in. We're going to substitute those in. So here is my capital A that I found up here. Here is my capital B that I found up here, plus C equals f of A. Now I can take that and solve all of that for C. So I have f of a over here. I subtract this term and this term. And notice here that I have distributed this a. And then I can clean that up a little bit. So I get C equals f of a minus a f prime of a plus 1/2 a squared f double prime of a. So this is C. So I have my a, b, and c terms. Right now they look pretty complicated, but we're going to see that it's not quite as bad as it may initially appear. All right, so this was my original quadratic model of f. All right, so I have ax squared plus bx plus c. Here's what we get when we make those substitutions. Here's my a. Here's my b. And that entire thing in the brackets there is my c. Now what I did here was I combined up, I'm trying to work toward combining up my like terms. Alright, so I have f of a, I'm going to write these in terms of increasing derivative, the order of the derivative is really increasing. So my f of a comes from here. My f prime of a times x comes from this times this x. Minus f prime minus a times f prime of a. That's that one there. All right, my 1/2 f double prime of ax squared comes from here. My a times f prime of a times x comes from here and here. And then my 1/2 a squared f double prime comes from here. So I'm going to take these f prime terms, factor out the f prime, and I'm left with x minus a. I'm going to take my second derivative terms and factor out the second derivative. I also have some here. So notice that I have a 1/2, so I've factored that out. This one didn't have a 1/2, so when I factor out a 1/2 f double prime of a, I have to put a 2 in there with this a and x that are left. Alright, so I've factored out the 1/2 f double prime. And then this last thing that I'm going to do here, that is a perfect square. So x minus 2ax plus a squared factors into x minus a all squared. So here's my quadratic model. So I have f of a plus f prime of a times x minus a plus 1/2 f double prime of a times x minus a squared. That's my quadratic model. All right. Now let's go to a cubic model. I want a cubic model now. We can see here that there's a certain pattern that we are taking, right? First derivative a minus x minus a to the first. Second derivative x minus a to the third. So I can use that pattern to tell me a little bit more about what's happening there. All right. We're going to work. I'm going to pause the video and start another one. We're going to work on the cubic model here in the next step.